So today's class is Computer Organization Module 3, Lecture 3. Now, last day we learned about what is cache memory in the memory hierarchy. Again, I am just recalling the things. Cache memory is a temporary memory which is in between the processor and the main memory. What is the function of the main cache memory? The function of the cache memory is to store a small portion of the main memory such that, and it is a high-speed memory, and it is stored such that to bridge the speed gap between the processor and the main memory. Okay, that means the portion of the main memory, which portion of the program in the main memory which is used again and again, if I put that portion into the cache memory, then the performance of the system will be up. Okay, so the thing is here that whenever we are storing the part of the program or data or instruction into the cache memory, there should be some logic. The logic is for at which address the particular program should be stored. Okay, we know the main memory address. You know that the main memory address is required for fetching the instruction and data from the main memory. Similarly, from the main memory, we have to know, as the main memory, we have to know what is our processor has to know what is the address in the cache memory. Clear? That means we have to generate some cache memory address by which processor can search or processor can check whether the data is present into the cache memory or not. If the data is present into the cache memory, we know that is called the cache hit. If it is not present into the cache memory, that is called the cache miss. Somehow we have to generate the address from the main memory. Generate the address means generate the address of the cache memory from the main memory. And this process is called mapping. See here it is written generation of the cache memory address from main memory address is mapping. And there is another thing. I have already told that processor will search the cache memory to check whether the data is present in the cache memory or not. How it will search? For searching, there some part of the address is used to find out whether the particular block is present into the cache memory or not. If it is not present, that means the cache miss. If it is present, that is called the cache hit. If it is present, that is called the cache hit. If it is not present, that is the cache miss. See, it will be clear from the next picture. See here in the right hand side, this 101110, these all are the address. What is the total number of addresses? See here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That means this is number of the address base is 12. So what is the total number address it can generate by the main memory is the 2 to the power 12. So this is the data which is written in the main memory. See, this is the main memory address and this is the main memory data. Here you can find out that the main memory is divided into certain block and each block contains 4 words. See, suppose this block. This is a line, black line. This is one block. So AB, 55, F0, FF. These all are the words and in the data, and these are the data in the word. That means here the main memory is divided into blocks and each block contains 4 words. So this is the main memory division. Left hand side you can see that is the cache memory. See here the operation is for the read operation in the cache memory. Now suppose the particular address, see here in the left hand side you see here the address is written as 101110000110. This address is generated by the CPU. Clear? Now CPU has to find whether the data is present into the cache memory or not. Clear? If the data is present into the cache memory, it will be hit, otherwise it will be missed. How it will find? See here the left hand side bits, these 2 bits are for the word because here each block contains 2 words, so 2 bits are required for generating 4 words, 2 bits. And the remaining bits, these are called the tag bit. So there is a particular section here in the cache memory that is called the cache tag memory, where the upper hand bits, the upper bits are stored here. Okay, suppose this address is generated, it will check the whole tag, whether whole tag memory, whether this particular tag, this is the tag, this is the word and remaining are the tags, to check whether the data is present into the main memory, cache memory or not. See, suppose it compare with this tag. See, this tag is equivalent to this tag 1011100001. That means data is present into the cache memory. This is called the cache hit. then it will go at the particular address. So what is the address here? 10. See, 10, this is the word address. See, this is the 10, and what is the stored here? This is the tag. It will point to this particular total whole word, and here in the word the address is 10. That means this address, the data is selected, and data out will be FF. That means this data will be out. Clear? See here, this is the particular data FF. This is the particular address, and corresponding to address, this is the particular address here, and here the left hand bits, here the address, but here the left hand bits, that means left hand 10 bits are used for the tag, and it is compared where the data is present in the cache memory by this tag. Okay, then if it is not present, then it will be hit, otherwise it will be missed. Suppose this data, this physical memory is generated 10, last one 101111000010. Okay, it will go here. So what is the word address here? 10 word address, and the left hand side it will be tag field, 10 bits tag field. So this is the tag field. It comes here, it finds out that no such tag is stored here. That means data is not stored here. That means that is the cache miss. What it will do, it will take the data 19, not the particular data, it will take the whole block into here, okay, into the cache memory, and it will store this tag here, such that the next time when this address is generated, it will search the tag, and if it obviously it can find the tag because it is already stored here, then it will get the data from the directly from the cache memory. So this is the read operation in the cache memory. Similarly, this is another write operation. In the write operation also, the thing is same. Here the address is divided into tag field, and the word address it will go here, and it will compare the tag whether the data is stored here or not. Yes, this tag is stored here 1011110001. This tag is this. Then it will go to the particular word is 10. That means this word we have to change this word. The data in is 88. Now this is a write operation. So data will be stored into the particular address here in the 88. Clear? So here this is the main memory. This is the cache memory, and see here the cache memory stores the whole particular block, not the single word, because this is the total block F488 particular for this address. For this address, the total block will be stored, not this particular data in this address. So this is the total block. Out of this block, only one word address is written here. So 88 is the final value. So this is the write operation in the cache memory. That means for writing or reading operation, first address from the main memory address, cache memory will find out what is the tag field. Then it will check the tag field memory to find out whether the particular data is stored into the main memory main cache memory or not. That means if the tag field is present here, cache tag memory, the data is present into the cache memory. If it is not present, data is not present into the cache memory. If it is present, it will be cache hit, data will be executed. It may be read operation or write operation. If it is not present, it will directly go to the main memory. It will take the whole block which contains the particular word, not the single word, whole block into the cache memory, and it will update the tag field such that in the next time when CPU generates the particular address, it will directly get the data from the cache memory. It don't have to go to the main memory. That means it will be a cache hit. So this is the operation of the cache. Now the question is how to generate this tag field and how to generate the address. That means how to know that whether the data is stored here or here or here or here or here. How computer will know? So that is called a mapping. That means generating this tag field and the cache memory address from this main memory physical address is called the cache memory mapping. Clear? So there are three types of mapping. Before I go into the mapping, first see this figure. In the figure, this is the main memory, you know. Here the main memory is divided into blocks. Last day I told about what is the block, how it is divided, logically divided into blocks, and each block contains 2 words. You can see here. So what is the total number of blocks here? B0 to B7, because there are 16 words. Each block contains 2 words. That means 2 into 8, it will be 16. So number of the block will be 8. Similarly, for mapping, The left hand side is the cache memory. The cache memory also should be divided into number of similar blocks. In this case, that is called the line, not the block. See, again I am telling, when we are dividing the main memory into a number of the sections, that is called the block. Here this is the B0 to B7, these are the block. Cache memory was also divided into number of the certain sections, that is called the lines. Here the line is L0, L1, L2, L3. Remember, here it is written size of the cache memory line is equal to size of the main memory line. What is the meaning? Meaning is that if each block contains 2 words, each line will also contain 2 words. If each block contains 4 words, each line should also contain 4 words. If it contains n words, each line should contain n words. See here each block contains 2 words. Here each line contains 2 words. Clear? So this is the organization of the cache memory with the main memory. Now we have to find out how to generate this line number. That means this block number will store here. Here we can store here, 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 or here. That means there are 4 lines. Any blocks can be stored in the any of the 4 lines. Now how to find out which block will be stored in which line? That means how to generate the particular line number from the block number of a particular set of program. Clear? That means from the block number we have to map the line number. Again I am telling, from the block number we have to generate the line number. Suppose the block number is given, we have to find out what should be the line number of that particular block. That means where the particular block in the cache memory should be stored. That is called the basics of the mapping. Now we know that main memory can be defined by a physical address. Clear? Physical address means 11111000. This binary address is the physical address. This physical address, last day we know that this physical address we can divide it as a block address and word address. This is the second one. We know that is the block address and second word address. If I go to the previous, see here, this is the block address and each block contains 2 words. That means here we require 1 bit. So block address and word address, this total memory is divided. Clear? This is the division of the physical memory. Similarly, from this physical memory, word address would be same. This block address again can be divided into 2. One is the left hand side upper bits is the tag field and another is called the cache address. See here, physical address we know. From the physical address we can generate the word address and block address. We know how to generate. In the last day's lecture I have told you. Now from the block address again we have to generate 2 address, not 2 address, 1 address and tag field. 1 address is the cache address and the remaining bits will be the tag field. That means this physical address ultimately divided into 3 fields. One is called the word address, another is called the cache address, and another is called the tag field. This is for the cache memory. And this physical address, same physical address can be divided into 2 fields. One is the block address and the word address. This is for the main memory or RAM. So this is the total division of the memory. All are the logical division. So there are 3 types of mapping. That means there are 3 techniques to find out the line number from the block number. Clear? Again, I repeat that 3 types of mapping means there are 3 techniques to find out the particular line number, cache memory line number from the main memory block number. When I tell about line, that is in the cache memory. When I tell about the block, that is in the main memory. So mapping means processor has to generate the particular line number from the particular block number. Now see, there are 3 types of mapping. All are very important and all have its advantage and disadvantage. First one is the direct mapping. Second one is the fully associative mapping. Third one is the set associative mapping. Now, see the direct mapping. In the direct mapping, the cache memory line number is generated by this formula. This is a very simple formula. The formula is cache memory line number is equal to main memory block number mod n. What is n? N is the number of lines in the cache memory. Again, I am telling you. Cache memory line number is equal to main memory block number mod modular operation n. N is the number of the lines in cache. Clear? if I give one example, it will be more clear. So see here, I have already told there are three fields. One is the word address, another is the cache line address, another is the tag field. See here, if the cache contains, if the block contains 4 words, what is the total number of bits required here? 2 bits, because 4 means 0001 1011. Clear? If the cache contains 8 lines, see here, if the cache contains 8 lines, number of the bits here will be 3, because 2 to the power 3 is equal to 8. So here 3, here 2. 5 bits are required for this. And the remaining bits, suppose the total memory size is 20. So 5 bits, this plus this 5. If the total number of the bits is 20, that means 20 minus 5, that means 15 number of bits will be required for making the tag. Clear? I have shown you the tag. That tag will be the remaining bits which is not required for the cache and cache memory address and word address. That means if the total memory number of the bits is capital N and the cache memory is small n and word address is W, that means capital N minus W plus small n is equal to number of the bits in the tag. It will be clear if I show one example. See, this is the one problem, it will be clear. In a system, number of the address bit is 4. Clear? That means what is the total number of, what is the size of the memory? 2 to the power 4. A block contains 2 words. Fine. A block contains 2 words means what is the number of the bits required for address each word in a block? 1 bit. 1 bit means 0 or 1, 2 words we can address. If a block address is 6, see here, this is not the physical address, this is the block address. Okay. Word address is 0 and cache contains 4 lines. What is the corresponding cache line address and tag field? See here. So line number from the formula we know 6. 6 is the block address, modular operation 4. Why 4? Because cache contains 4 lines. So 6 mod 4, it is the 2. That means what is the line number? Line number will be 10. Clear? That means if I go previously, if our number is 6, okay, it will go to the line number 10. That means this line, this is 00, 01, this is 10. That means the particular 6, that means this block 6 contains means this line, this is the this line, this is the 6, that means B2 block, B3 block, okay, is a, if it is B3 block, it will be go to the line number 2. Clear? So that means that if the block number is 6, this is the B6 blocks, it will be go to the line number 2. Okay, 6, because this is the 6, this is the block number, and this is the particular line number is the L2. That means this total block will go to this total line. So this is the mapping. Again, I am going here. So line number 2. Now the block address, we know what is the binary of the 2. 110. Binary of the 6, 110. Line number, it is already told 10. So this is the line number. This line number we have got from here. And what is the tag field? If this is the line number and this is the block number, so this 2 is the line number, 10 is the line number, 10 is the line number. Clear? Previously, if I go here, so these 2 required for the line number, 2 bits are required. Okay, this is the word is 1, this is 2, and remaining, what is the remaining? Remaining is the 1 bit, tag is 1. Clear? So our answer is here the tag field is 1 and line number is 10. Now you can ask me what is the original physical address. See here. What is the word address? Word address is 0. I put the 0 at the right hand side. What is the line address? Line address is 10. Then I put 10. Clear? What is the tag field? Tag field is 1. I put 1 here. That means the original physical address of the data is 1100. This is the original physical address. This is divided into block address 110 and word address 0. Okay, block address 110, word address 0. Again, it is this block address is divided into 10 as a line address. 10 is the line address, and the left hand upper bit tag field is the 1. So this is the division in the direct mapping. Clear? Now there is a disadvantage in the direct mapping. What is the disadvantage? Disadvantage in the direct mapping is that here what will happen, processor first generate this physical address. From this physical address directly it can find out what is the cache memory address. See, if I divide this, we find this address without using this operation. Directly from the physical address we know these 2 bits is for the cache memory. So if you directly go to the cache memory address and check whether the tag field is present, that means in this case this is 1 is present in the tag memory or not. If it is okay, if match in the tag field, that means data is present, it will be hit, otherwise it will be miss. So what is the advantage? Advantage is the speed of the mapping is the highest because we directly know what is the address of the line and we go at that line and then we check the tag field. Clear? You don't have to go through the whole tag data. We particularly go to the particular tag field and particular address of the tag field. That means, see here, I'm seeing here, I'm showing here. See here, it will go to the particular address. 1 minute. Yes, here it will go to the particular line number. From this block number is generated particular line number, then it will check the tag field whether the data is present or not. If the tag is matched, that means data is present, it will generate it will execute the data. But there is a problem. What is the problem? See here, disadvantage is that 2 or more block address may generate the same line address. Example, suppose first block address is 6, number of the lines is 4, 6 mod 4, line address will be generated 2. Again, suppose at the same time, after some time, another block address is generated, that is 10. So what is the line address? 10 mod 4, it is again 2. See here, line address is 2 here also, line address is 2 here also. That means both the block address is generating the same line address, though their tag field will be different. But when one line is already occupied by some data or instruction, processor cannot put the another data. So it has to wait and there is a chance of collision. Even if all the places are empty, okay, suppose these 2 address only generated, these 2 address compete only for the 1 line number, even if all the line numbers are empty. So there is a chance of collision. Even if the spaces are empty in the cache memory, processor cannot put the data because processor is using the direct mapping. Clear? So this is the disadvantage of using direct mapping. There is a chance of collision, and the advantage is the speed is the highest among all mapping because it can directly find to the particular address and check at the particular address. It will check the tag field whether the data is stored there or not. So this is the disadvantage, and advantage is the speed. See here, tag when the block is 6. See here, when the block is 6, the tag field is 0 1. Clear? Suppose there are 4 bits there, tag field is 0 1 because this is 2, 1 0 is 2, 1 0 is 2. But here see the tag field, here there are 10, tag field is 1 0. Tag field are different but line address is the same. That is the problem. Clear? So its speed is the highest, I have already told. To solve the problem, another mapping is used, that is called fully associative mapping. What is the concept of fully associative mapping? In the fully associative mapping, no address is generated. Processor finds the empty space into the cache line. If any line is empty, it will put the particular block into that line. It will not check whether, it will not use any types of algorithm for generating the address. Clear? That means suppose here in a system, a number of the address bit is 4, same problem. A block contains 2 words. If a block address is 6, word address is 0, and cache contains 4 lines, what is the corresponding cache line address and tag field? Here the line number, any number if the line is empty. That means if the space is empty, it will put the particular data here. It will not check the particular address. So if this is the block address, okay, if this is the block address, as there is no cache address is 0 there, the whole block address will be equivalent to the tag field 110. Clear? Again I am repeating. Here in the previous case 10 was the cache memory address line number because processor is using direct map cache memory. Here there is a fully associative cache memory. There is no address generation of the cache from the physical memory. So whole block address will be stored as a tag. So what is the problem? Problem is that, what is the advantage? There is a least chance of the collision, because when one line is empty, processor will put the particular block in that line. There is no chance, but least chance of the collision. Collision will only happen when there is no empty lines in the cache. Otherwise, there is no chance of collision. But the problem is, as there is no addresses generated in the cache memory, for searching the tag field, processor has to search the whole tag memory. Okay, that means that will be a sequential search. First, it will search the first position, tag is matched or not. If it is matched, okay. Not matched, again go to the next. Again go to the next, because it does not know the address. If you don't know the address, you have to search for the whole memory. Clear? See here, again the physical address is same. See the significance. Suppose the block 0. Block 0 store in the line number 0. It is empty. At first it is empty, suppose. Then comes B1. Line 0 is already occupied. B1 will store into the line 1, line 2, or line 3 randomly. Suppose it is stored in the line 3. Then comes suppose B4. It stores into the line L1. Then suppose B6. It stores into the line L2. There is all is occupied. Now suppose one address is generated and processor has to search whether the data is present in the cache memory or not. So it will generate the tag field. It will search the tag field for this line number. If it is matched, cache it. If it is not matched, this is not a cache miss. It will go here, okay, to check whether the tag is present. If it is present, okay. If it is not present, again it has to go to the next line number. Again check if it finds the tag, it is okay. If it is not found, again it will go here. Here it finds, that is the cache hit. If it is not found here also, that means it is a cache miss. Clear? That means processor has to search the whole cache memory to find a match for the tag. That means to know whether the tag is present into the cache memory or not. But in the previous case, in the direct mapping, from the block number, it is first going to the particular line number, and then it is checking whether the tag is present or not. If it is present, that is hit. If it is not present, that is miss. We don't have to check the whole cache memory. But in this case, as there is no address and the tag field is equal to the block address, number of the bits in the block address, so it has to search the whole total cache memory. What is the advantage? Advantage, obviously there is no chance of the collision, because whenever there is an empty space, it will put the data there. Number one. Number two, disadvantage, it is time consuming. Why? Because it has to search the sequentially the whole cache memory to find the tag. Okay, in the previous case, it will particularly go to the particular address, then it is checking whether the data is present or not. But here, to check whether the data is present or not, it has to go for the whole memory. So this is the disadvantage of using the fully associative memory. Clear? So to solve the problem, yeah, I have already told searching time is the highest, least chance of the collision. Another mapping is used. This is in between the direct mapping and fully associative mapping, that is called the set associative mapping. Clear? Here what happens? Here the cache memory is again divided into a number of sets. I have already told it is divided into the number of lines. Again it is divided into number of sets such that each set contains a number of the lines. If each one set contains 2 lines, then it will be called a two-way set associative. If it contains 4 lines, that will be called 4-way set associative. See here, the cache memory number will be J mod M. What is J? J is the block number. M is the number of set into the cache memory. In the direct mapping, it was number of the lines in the cache memory. Here it is the number of the sets into the cache memory. J is the block number, M is the number of the sets in the cache memory, and I is the cache memory set number. Clear? Now see here, it will be clear from here. See, this is the right hand side is the main memory. It is divided into block. Each block contains 2 words. Again, the left hand side, it is divided into lines number. This is a cache memory. Each line contains 2 words. See here, this is one line, this is L1 line, this is L2 line, these 2 words in the L3 line. These lines again divided into sets. See here, each set contains 2 lines. That means set S0 and set S1. Now in this mapping, in the set associative mapping, what happens? From the block number, particular set number will be generated. In the direct mapping, from the block number, we are generating the line number. In the fully associative mapping, from the block number, no address is generated. It can be randomly stored in any address. But in the set associative, from that particular block number, particular set number will be generated. Clear? Now, what is the formula? In the formula, we will generate. See, again, I am going to the formula. In the formula, we will generating the particular block set number from the block number, not the line number. Clear? So this set number will be generated. And here, what is this called? This is called two-way set associative because it contains 2 lines. It contains, sorry, 4-way set associative because each set contains 4 lines. Again, I am telling this system is called 4-way set associative because two-way set associative because each set contains 2 lines, L0, L1. Then set 1 contains L2, L3. This is called two-way set associative. If each set contains 4 lines, it will be 4-way set associative. Now, question is, what is the advantage of using this? Here, this is in between the direct mapping and fully associative mapping. Why? Because after here, it will go to the directly to the set number. Clear? It will go to the set number. And within the set number, it will put the block number anywhere. Okay. So the mapping of the set number is direct. Within the set, it is fully associative. Again, I am repeating the thing. Here, set number is generated. That means block will directly go to the set. Fine. Within the set, it will randomly, if there is an empty space, it will put the data. That means generation of the set is like direct mapping, and within the set, it will be a fully associative mapping. So this is the advantage. That means it has the advantage. It is taking the advantage both the direct mapping and the fully associative mapping. So set in the most modern computer actually use this set associative mapping. Clear? So here one example is given. In a line number, this a block contains 2 words. If a block address is 6, word address and the cache contains, and this is a two-way set associative, what is the corresponding cache set address and tag field? So the set number is 6. Set number is 6 mod. What is the total number of set? We have seen 2. So 6 mod 2, 0. That means the particular block 6 will go to the set number 0. And within the set, it can, if there is an empty space, it can put the data anywhere. Clear? So what is the block address here? Block address is 110, just like the before. And here, what is the tag field? Tag field, because this is 0, this 0 is the set number, and the remaining is the tag field. So remaining data is 11. So this is the tag field. Clear? Physical address, you know. Disadvantage, it takes the advantage of both the direct mapping and indirect mapping. Clear? So